All right. Hey everybody. I hope you're all doing well. I hope you're handling this whole situation as best you could. This is weird. It's totally weird teaching to a camera, and it's a weird setup we got here, but I spent the last few days getting a home physics studio for you, so you could see my face while I teach you things. It's been a headache. We're still working on the lighting. As you can see, I'm not really that bright, but we're gonna do the best we can. As time goes on, I want to start teaching. I want to start doing more videos where I'm teaching the content as opposed to these short videos where I'm just doing some problem solving. But over the weekend, I'm going to start compiling more of those types of videos. For now, this is kind of a test. I'm seeing if the whole system works out. Hope you enjoy the video. Hope you're doing well. Okay, so here's the situation that we're going to try to solve. We have this system where we have a disk rotating, with disk with a rotational inertia of I1, rotating at some angular velocity omega naught. This disk above disk 1 is not rotating initially, but what's going to happen is while this disk is rotating, disk 2 is going to drop down on disk 1, and then the whole system is going to rotate together. Our goal is to figure out how fast that the system is going to rotate after the collision takes place. Some things that are given: I2, the smaller disk, has 1/3 of the angle of the rotational inertia of disk 1. Okay, so how are we going to solve this out? The concept that we're going to utilize here to figure out the situation is conservation of angular momentum. And just like with linear momentum, when we're looking at angular momentum, the total angular momentum of the system before an event takes place has to be equal to the total angular momentum after the event takes place. That's as long as there's no external torques acting on the system. So what we're going to do is we're going to analyze the total angular momentum of the system before this collision and after this collision, and use that to figure out how fast this system is going to rotate. Is this going to speed up? Is it going to slow down? And if it does, how much is it going to speed up? How much is it going to slow down? All right. So first, looking on the left side of the equal sign, we're going to look at the angular momentum of the system before the disk falls on disk 1. So we want to see what bodies here actually have angular momentum. As we can see, disk 2 is not rotating, so all the angular momentum here is manifested in disk 1. We know that angular momentum is equal to the rotational inertia of that object multiplied by the angular velocity of that object. Remember that angular momentum is a vector. So looking at object 1, we can see that it has rotational inertia I1 and it's spinning at some omega naught. So initially, we only have I1 omega naught. If disk 2 is rotating, we would add that on to this and say that it's disk 2 rotating at I2 with whatever the angular velocity of the disk 2 is. But here it's only disk 1 rotating, so this is our total initial angular momentum of the system. This is weird. This is so weird, teaching to a camera. Okay. So now on the right side of the equal sign, we're going to be looking at the final angular momentum of the entire system. So we have disk 1 doing some rotation and disk 2 doing some rotation. But the thing here is when they collide, they stick and they start rotating, they're going to be rotating at the same final angular velocity because they're connected to one another. So, just going to erase this. Like, this is nice, right? Got this whole setup here. All right. We have disk 1 rotating with the final angular velocity omega, and we have disk 2 rotating with that final angular velocity omega. Again, we're trying to solve for the final angular velocity in terms of the initial angular velocity. So here's our setup. Now we want to plug in what we know. We know that the rotational inertia of disk 2 is 1/3 that of disk 1. So now we can plug that in here. I1 omega naught is equal to I1 omega plus 1/3 I1 omega. From here on out, all we have to do is simplify and try to solve this in terms of the final angular velocity. Okay. So what I want to do is I'm going to pull out the omega. I1 omega naught is equal to I1 plus 1/3 I1, parentheses, multiplied by omega. We can divide that over to the other side, and we see that our final angular velocity is equal to I1 omega naught over I1 plus 1/3 I1. Now, something we could have noticed early on, but we see I1 show up in all these terms, so that could actually cancel out. And now we're going to get some kind of fraction, some kind of coefficient for omega naught to see how it relates to that final angular velocity. So now this is 1 plus 1/3, which ends up being 4/3. 1 over 4/3 is equal to 3/4. So as we can see, based on this setup, that the final angular velocity of this system is going to be about 3/4 of the initial angular velocity. And we know that because angular momentum is conserved in all cases where there's no external torques acting on the system. I hope you predicted that it was going to slow down in this case because we added rotational inertia to the system. So if we increase the rotational inertia, we know that the angular velocity should decrease. And there's the work. I'll pause the video or something, take a look. All right, so that was our test video. I hope you enjoyed it. I'm going to try to do more videos, longer videos, and more instructional videos in the future. Take it easy, stay safe. Bye. Good?
Yeah, you press the little red button.